All right, let's jump right into this explainer and begin our descent into one of the most fascinating and frankly extreme environments on Earth. Today, we're taking a journey into a realm so totally alien to our everyday lives that it literally redefines the boundaries of biology and physics. We are, of course, talking about the Mariana Trench. Now, forget the familiar sun-drenched coral reefs you usually see in marine biology. We're heading way down to the Challenger Deep, which is nearly 36,000 feet beneath the surface of the Pacific Ocean. This is a world that completely challenges our fundamental understanding of how life even operates, presenting us with a massive uncharted frontier that we're really just now developing the technology to properly explore.
It's actually a stunning paradox that we know vastly more about the cold, infinite vacuum of outer space than we do about the deep, hidden trenches right here on our own planet. Think about it. We're constantly mapping distant galaxies and getting these high-def images from Mars rovers, yet our own seafloor remains this profound mystery. But there's actually a very good, purely physical reason for that. Engineering a spacecraft to withstand a 1-atmosphere pressure difference in the vacuum of space is, fundamentally, a way easier physics problem than building a submersible to survive a 1,000-atmosphere pressure differential at the bottom of the ocean. Plus, the electromagnetic waves we use to map the cosmos, they travel endlessly through a vacuum. But radar and visible light, they get completely absorbed by seawater within just a few hundred feet.
So as we metaphorically dive deeper into the trench, we immediately run into the stark physical realities that govern this whole ecosystem. The defining characteristics down here are crushing pressure and complete blackness. To put that pressure into perspective, at the bottom of the Mariana Trench, you're dealing with roughly 16,000 pounds per square inch. That is literally the equivalent of having dozens of jumbo jets stacked directly on top of you. Under those extreme conditions, basic chemistry actually begins to change. Proteins fold differently, and standard cell membranes would simply turn solid. And because sunlight has absolutely no way to penetrate these depths, the environment is permanently deprived of solar energy. It's a world operating in perpetual midnight.
Now, the crucial point here is that this extreme physical reality forces us to completely rethink how an ecosystem can even function. When you strip away everything we consider absolutely necessary for life, namely sunlight and photosynthesis, you don't just get an empty, lifeless void. Instead, you get this completely unique, alternative ecosystem driven by a totally different set of biological rules. Down here, life finds a way through processes like chemosynthesis. This is where specialized bacteria actually convert toxic chemicals and methane from deep-sea hydrothermal vents directly into usable cellular energy. It's a brilliant reminder that life doesn't actually need a sunny surface to thrive. It just needs an energy source, even if that energy is coming straight from the planet's volatile core.
Okay, so how do researchers actually monitor this completely inaccessible world? Well, since we can't easily send human eyes down there, we have to rely heavily on our ears. Our main tools for this are highly specialized underwater microphones called hydrophones, which are deployed by organizations like NOAA. These devices are incredible. They're encased in thick titanium just to survive that crushing pressure we talked about, and they're tethered right to the seafloor. They just sit down there in the freezing dark, passively recording gigabytes upon gigabytes of deep ocean acoustic data. Scientists then run these massive audio datasets through complex algorithms to filter out the normal stuff, like tectonic shifts or regular whale songs, purposefully hunting for anomalies in a soundscape that we simply cannot see.
And man, what those hydrophones have actually captured over the years is nothing short of extraordinary. The deep ocean is just filled with unexplained acoustic anomalies that initially completely baffled scientists. Take the famous bloop, recorded back in the 1990s. This was an ultra-low frequency, massive sound that was so incredibly loud, researchers first hypothesized it had to be made by a marine animal way larger than a blue whale. Now, later research did link it to massive ice quakes in the Antarctic, but still. Or consider the Western Pacific biotwang. This is a complex, 3.5-second call with this bizarre, metallic, almost mechanical overtone. While researchers now strongly suspect it's a highly unusual call from a bride's whale, discovering such a synthetic-sounding echo in a supposedly empty abyss fundamentally challenges our baseline assumptions about deep-sea communication.
But the mystery deepens even further when we shift from what we hear to what we actually see. When remote-operated vehicles, or ROVs, manage to finally shine their floodlights down into this abyss, they reveal biological wonders that look entirely alien. For example, researchers have found xenophyophores. These are single-celled organisms surviving in the sediment that literally grow to the size of a human hand. A single cell. Or look at the Mariana snailfish, which is the deepest known fish ever recorded. You'd think it would look like a heavily armored tank, right? But actually, scratch that. It's small, translucent, and completely scaleless, just gracefully swimming through that intense pressure at 26,000 feet. Every single time a camera goes down, we end up documenting bizarre organisms that rewrite the textbooks on evolution.
So I want you to think about this for a second. How exactly does a delicate, translucent snailfish withstand conditions that would instantly crush a military submarine? The answer comes down to some truly spectacular biological adaptations at a microscopic level. To survive that immense weight, many deep-sea organisms use specialized molecules called piezolites. A really common one is TMAO. This chemical basically acts like microscopic scaffolding, stopping water molecules from forcing the animal's proteins to collapse under the pressure. And fun fact, it's actually the high concentration of TMAO that gives deep-sea fish their distinctively strong fishy odor when they're brought up to the surface. On top of that, these creatures pack their cell membranes with high levels of unsaturated fats. This keeps them fluid and flexible, preventing them from freezing solid like a stick of butter in the cold, pressurized depths. To really wrap your head around the scale of the mystery we're dealing with here, just look at the sheer volume of water that remains entirely unmapped. A staggering 95% of the global ocean volume is still completely unexplored by human beings. 95%! It is the largest single biome on Earth, and we have barely even scratched the surface. Those piezolites, the weird single-celled giants, the metallic-sounding whale calls, these are just the anomalies we've accidentally stumbled upon within a tiny fraction of a percent of mapped territory. It's almost a statistical guarantee that every single time a deep-sea ROV is launched, it's going to encounter a species completely new to science. The deep ocean isn't some empty void. It is a massive, uncatalogued library of Earth's biology.
Facing that massive lack of information is a genuinely humbling reality. The vastness of the unknown is literally crashing against our shores every single day. But rather than viewing this as something terrifying, we should really see it as awe-inspiring. We don't necessarily have to look up to the stars to find the final frontier of scientific discovery. It exists right here, beneath our feet, on our own planet. The Mariana Trench and the deep ocean as a whole is the absolute ultimate frontier for human curiosity. It represents this unparalleled opportunity to discover new chemical compounds, totally new evolutionary pathways, and entirely new branches on the tree of life.
So as we wrap up our exploration today, I want to leave you with one incredibly provocative thought to chew on. If the tiny little fraction of the ocean we have managed to survey holds such unbelievable extremes, crushing pressure, absolute blackness, mechanical-sounding acoustic anomalies, and cellular adaptations that completely defy logic, what is truly thriving out there in the unexplored 95%? It really forces us to pause, look out at the water, and recognize that the greatest mysteries of our world are still hidden deep in the dark below. Thanks so much for joining me to unpack this incredible environment today, and as always, keep questioning the unknown.